Salam and welcome everyone. So today we're going to be working on the question on the screen that says estimate the freezing point of 200 centimeter cube of water sweetened by the addition of 2.5 grams of sucrose. Treat the solution as ideal. So this is a question from the Atkins Physical Chemistry 11th edition from chapter 5b, question 4a, and we're told to determine the freezing point of 200 centimeter cube of water. So we have in this question the volume of water to be 200 centimeter cube, sweetened by the addition of 2.5 grams of sucrose. So it was sweetened by the addition of sucrose. So the mass of sucrose, which I'm going to denote as SUC, is 2.5 grams. And they said we should treat the solution as ideal. Now, before we go forward, remember what we actually asked to determine is the freezing point of 200 centimeter cube of water sweetened by the addition of 2.5 grams. So this is going to be the freezing point after mixing as occurred, because you have the freezing point of just water by itself, pure water, before it was sweetened. And then after sucrose has been added, we have the freezing point of solution after the addition of sucrose to the water solvent. Now, understanding this, I want to highlight something that will be very important for us in this question. I want to first of all let everyone know that we have a solute here, and that solute is sucrose, okay? And then we have the solvent here, and that solvent is simply water. So the solute is sucrose, which we denote as SUC, and then the solvent is water. You see the reason why I'm writing this out in a couple of more steps. So now, reading all what we've read, we want to determine the freezing point of water of the solution, basically, after mixture has occurred. So we have to use a formula called the freezing point formula, or freezing point equation, or freezing point depression formula. It is simply change in T sub F is equal to K sub F multiplied by B. So this here is called the freezing point equation, or the freezing point formula. So that is basically what this is. This is the freezing point equation, or the freezing point formula, where changing T sub F, okay, is the change in freezing point. And of course, the unit for this is the unit for temperature, which is just simply Kelvin. I want to quickly talk a little bit more about the change in freezing point. As you guys are aware, if there is an initial phase or a before phase and an after phase or a final phase, there is usually a change in that value. So changing T sub F is just basically the difference in temperature, or the difference in freezing point if you want to use that particular language. But it's really just the difference in temperature before mixing occurs and after mixing occurs. So changing T sub F is the changing freezing point of the, so changing the temperature of the freezing point after mixture has occurred, while there was a before that had happened, which is just the freezing point of the solvent. Then after is the freezing point of the mixture or the solution. So that's it. Then you have K sub F, which is just simply the freezing point constant of the solvent. So just like we know that constant values are constant and they have like an exact value. For example, the speed of light is 3.00 times 10 raised to the power of 8 meter per second. You have the acceleration due to gravity, you have it as an exact value. You have the gas constant 0.08206 or 8.3145, depending on the unit you're using. You see that these are constant values. So what this is telling you is that the is always an exact number that is a constant for the freezing point of any solvent. In this case, our solvent is actually water. So basically, it is the we have a freezing point constant for water. So next we have B, which is just simply what we know to be molality. So if you remember from your Gen Chem, what is molality? You're dealing with here the molality of the solute. Let me write that down first before I go into detail what molality is. Molality, if you remember from Gen Chem, and if you don't remember from Gen Chem, this is a great refresher. Molality is simply the mole, okay, of solutes, or the number of moles of solute divided by the mass of solvent in kilograms. So the mole divided by the kilograms. So the B value, moles of solute, mole divided by the mass of solvent. So the unit is usually in mole per kilogram. So now looking at all of this information, we now have to go back to our question. We see that we're only given you see that we're only given the volume of water as well as the mass of sucrose. So basically the volume of the solvent and the mass of the solute. We're not in any way, shape, or form given the mole of the solute. We're not given the mass of the solvent. We know the value for K sub F to be the freezing point constant, and it's going to be an exact value. So let me quickly write this down. K sub F, when you Google it or you check the back of the resource section in the Atkins Physical Chemistry 11th edition textbook, you see that the case of F for water, okay, is just simply 1.86 Kelvin kilogram per mole. So this is the value that you need. So we have successfully determined what K sub F is, but we do not have the value for B because we're not given. Neither do we have the moles of solutes. Neither do we have the mass of solvent. So we have reached a point where we don't even know what B is. But then again, we are chemists. So let me write what B is again. We have mole of solute, okay, divided by mass in kilogram of solvent. Even though we're not given the value for B, the value for number of moles of solute or mass of solvent, one thing we were given when we go back to our question is the volume of water as well as the mass of the solute. So remember, we're told the mass, okay, of sucrose, and again, sucrose is the solute, is 2.5 grams. We're also told the volume of water to be 200 centimeter cube. So therefore, we have to determine the number of moles because we do have the mass of the solute. And if you remember in Gen Chem, number of moles of a particular compound, molecule, substance is just simply the mass of that molecule, compound or substance, divided by its molar mass. So in this case, we have the number of moles of sucrose, okay? Number of moles of sucrose is going to simply equal the mass of sucrose divided by the molar mass of sucrose. So this is what it is. So the mass of sucrose is just simply 2.5 grams. The molar mass of sucrose is simply 342.30 gram per mole. I want to quickly mention something to you guys just because somebody may be wondering, how did she get that? Well, I just Googled it, honestly. You can also, if you choose to do the step by step of determining molar mass, then that is all up to you. The reason why I did not need to show it is just because this is thermodynamics, it's an advanced chemistry course. You do not need to write out and solve for the molar mass of anything just because you're in a more advanced level and it does not really do anything to what you're working on. So it's possible that if you had an exam, your teacher can just give you the molar mass of sucrose, or they can give you the molecular formula and you can quickly solve for it. So for those of you who would like your questions detailed, because everyone has the way they learn, the molecular formula for sucrose is just simply C12H22O11. So this is simply the molecular formula for sucrose. So if you choose to do, 12 times 12 plus 1 times 22 plus 16 times 11, that's all up to you. I feel like that is just a waste of time. But if you are required to do it in an exam, please do not hesitate to do it. But in process of problem sets I'm studying, I don't think it's necessary for me to write that down because we're dealing with an advanced course. And yeah, you may also be given. So yeah, that's it. That's the reason why. Honestly, I don't want to confuse anyone anymore. The molar mass of sucrose is just simply 342.30 gram per mole. So you cancel out the grams, Then you have 2.5 divided by 342.30. When you do that in your calculator, you end up getting 0.00730 3535 mole. Okay, so we have successfully determined the number of moles of sucrose. So this is done. Now we have to determine the mass of solvent in kilograms. So basically the mass of water in kilogram. So the mass of water in kilogram is what? Now again, we're going to go back to Gen Chem. We've gone back to Gen Chem like multiple times already in this question, and you're going to keep going back to Gen Chem in physical chemistry, honestly. you're going to go back to some high school chemistry basics. Yeah, we're going back to Gen Chem. So we have the mass of water in kilograms, and we're told to determine it, but all we're given is the volume of water in centimeter cube. So 200 centimeter cube. So going back to Gen Chem, we know that to go from volume to mass, or mass to volume of a particular liquid, we're going to have to use its density. Okay? We're going to have to use its density. So, therefore, in this case, we're trying to determine what mass is after we've given the volume. So, remember, density is simply mass over volume. And of course, to determine mass, you're just going to end up with mass is equal to density times volume. And we're going to make it specific to this particular question. So, the mass of water is equal to the density of water multiplied by the volume of water. So, yeah, that's it. Now you're going to be thinking, okay, let's substitute. I want to quickly mention a major important concept before we go ahead to do this question. You know that we're told to determine the density of water. What a lot of students make mistake with is that they pick the density of water at room temperature. Remember, this question is a freezing point question, aka we're dealing with the temperature of water at the freezing point, aka the temperature is usually 0 degrees Celsius. So we cannot just use the density at 25 degrees Celsius because the density is dependent on temperature. So if the temperature is different, the density is going to be different, meaning the density of water at 25 degrees Celsius is different from the density of water at 0 degrees Celsius. In fact, the density of water at 0 degrees Celsius is going to be different from the density of water at 15 degrees Celsius or 10 degrees Celsius. So even though it may not be more change in the value, it's very important to know that in this case, we're going to be dealing with the density of water, okay, at 0 degrees Celsius because we're dealing with freezing point. So therefore, the density of water at 0 degrees Celsius is just going to be equal to the density of water is 0.99984 gram per cm cube. And we're going to substitute it into here, so into this value. So we end up with here, the mass of water is going to end up becoming 0.99984 gram per cm cube multiplied by the volume of water that we're given in this question, which is just simply 200 centimeter cube. Okay, of course, we cancel out the centimeter cube here, cancel out the centimeter cube. 0.99984 multiplied by 200, which is just the mass of water, is simply 199.968 grams, which is just, yeah, that's it, the mass of water. But then again, remember that when we go back to our question, we've determined the mole of solute here, and then we are determining the mass of solvent, but it is the mass of solvent in kilograms. But what we have here is the mass of water in grams. So we have to go from grams to kilograms. So we're basically going to divide by 1000. And when we do that, the new mass of water, okay, in kilograms, simply just going to be 0.199968 kilograms. So this is going to be what we use. So therefore, B, okay, remember what B is number of moles of solute, so number of moles of sucrose divided by the mass of water, okay, in kilograms. So going up here, that is just what I'm doing. See, number of moles of solutes and then mass of solvents in kilograms. So we have determined the number of moles of sucrose to be 0.0730355 mole. So I'm going to write them down here. So you have the value for B is just 0.00730, okay, 3535 mole, okay, divided by the mass of water in kilograms, which we just solved, and that is just simply 0.199968 kilograms. So B is simply 0.00730 3535 divided by 0.199968 is going to simply give you 0.0365232, okay, mole per kilogram. So we have the value for B. And remember, we need to substitute into this equation, changing T sub F is equal to K sub F multiplied by B. So remember, change in T sub F is equal to K sub F. Okay, remember that is of water because it's the constant value for the solvent multiplied by the value for B, which is the solute, in this case SUC. So we just substitute. Change of F is just simply 1.86 Kelvin kilogram per mole. Okay, just like we have here. Just like we have seen up here when I wrote it down. Okay, I think I wrote it down. Yeah, I wrote it down right here. So we're going to substitute that, which is what I just did. Okay, multiply by the value for B sucrose, which is just simply 0.0365232 mole per kilogram. Okay, of course, cancel out the kilogram, cancel out the kilogram, cancel out the mole, cancel out the mole. So what you have here is just Kelvin. So changing T sub F is simply going to be 0.0, okay, 6793307 Kelvin. So we multiply the 1.86 by the 0.0365232, and we end up with this value for changing T sub F. So you can see that we've done a lot. And some of you may be wondering, yay, we're so done. We are beyond done. This is correct. Let us move on. My work is still not done, and the reason is simply because of I need to explain to you a concept, and then when you understand that concept, you will realize well our work is not done, and we have a few more steps in order for us to actually get the final answer. So those of you who are already used to the freezing point equation, you would understand this a lot better or understand my reasons why. But I will try to put everybody on the same page. Remember, the question is asking us for the freezing point of 200 centimeter cube of water sweetened by the addition of 2.5 gram of sucrose. So what we're actually supposed to determine is the freezing point temperature after mixing has occurred. But this change in T sub F is just the difference in the temperature value before and after mixing has occurred. Before mixing has occurred as well as after mixing has occurred. Now, before we go ahead, let me quickly explain something to you. So this is a container and this is the same container. So before mixing, you have water, okay? You have water, cold water at 0 degrees Celsius. So we have pure water at 0 degrees Celsius. Then after mixing, which is after the addition of 2.5 grams of sucrose, we end up with sucrose plus water. Okay. And what they're actually asking us is what is this new temperature? I want to quickly teach you guys something in the concept. As I explained earlier, freezing point equation can also be known as freezing point depression. Anytime that you have a pure solvent, in this case, we have pure water solvent, okay, after the addition of the solute, in this case sucrose, we end up with not a pure water solvent anymore. We end up with a sucrose, okay, water solution. So it went from being a solvent to a solution. Now, understanding it fundamentally in chemistry is important for you to know that anytime a solvent exists or a liquid exists and it's pure, meaning the only thing, for example, in case of benzene, naphthalene, um, methylbenzene, acetone, all of these things are solvents, just like water. They have the value for their freezing point. The freezing point of water is 0 degrees Celsius. They all have their own unique value. But in a situation where a solute is added to their container or into them to make a mixture, there is going to be a lowering in the freezing point value. So that is just why they call it freezing point depression. If you start at a particular temperature for whenever you're dealing with a pure solvent, right, or pure liquid, if you add anything, that thing makes that pure solvent to become impure and makes it a solution, hence decreasing the freezing point temperature. Meaning, if it's taking 0 degrees Celsius, for example, to freeze water, expect that the value of the freezing point after mixing has occurred or after the addition of a solute is going to actually be less. So expect a lesser value than 0 degrees Celsius. So this is what this is teaching us. This is just like if you do a lot of organic chemistry in the lab, for those of you who are chemistry majors, you would really understand this concept because you're going to be seeing it physically. So that is basically it. Freezing point decreases whenever there is mixture that occurs between a pure solvent and a solute. So yeah, that's basically it. So therefore, the temperature of the freezing point after mixture has occurred is simply just going to be the temperature of the freezing point before mixture. Okay, so basically the temperature, the freezing point value of the pure solvent minus the change in temperature, or change in temperature, understand, change in freezing point, whatever you want to call it, change in T sub F. So the temperature of the freezing point after is just going to be, what is the temperature or the freezing point before mixture? So basically, what is the freezing point of the pure solvent? We have water here, that's 0 degrees Celsius. Of course, we have to convert that to Kelvin, which is just simply 273.15 Kelvin, minus the freezing point change value that we calculated, 0.06793307 Kelvin. So we write that down as well. 0.06793307 Kelvin. When you subtract them after, it's just simply going to be 273.0820 Kelvin. And of course, T sub F after is just simply just going to be 273.08, because we have to put our final answer in two decimal places. So 273.08 Kelvin. As you can see, the value after mixing is actually less than the value of the pure solvent. So it went from 273.15 and decreased in value to 273.08, confirming the concept I just explained earlier with the diagrams. So yeah, if you do have any questions, suggestions, or concerns, please put it in the comment section. If you're a student who is struggling in any of your STEM-related courses, please do not hesitate to email me. I help students succeed in all your STEM-related courses, whether they're in middle school, high school, and college, by my way of tutoring and mentorship in order for them to succeed in academia. If you have an interest in just trying my sessions with me, I am 100% ready to go and to teach you. So I wish you guys all the very best. Assalamu alaikum wa rahmatullahi wa barakatuh.